Hi everyone, I'm very excited that we're about to start our first 3D Hubs live webinar. My name is David and I'm your host today. Today with Dylan, we will be answering your questions in the chat. Our presenter today is Alkaios. Alkaios is our in-house 3D printing expert. He has a PhD in additive manufacturing and a lot of expertise and knowledge in the area. The stage is all yours.
Hello everyone, my name is Alkeos, and today we're going to speak about 3D printing, additive manufacturing. We have prepared a lot of slides for you, and there will be 3 sections. We're going to start with a short overview of the latest trends in the 3D printing industry. Then we are going to speak a bit about the key considerations that you have to take into account before you go to production, and then we will cover the ideal use cases for each 3D printing process. First, though, let's start a little bit with a short introduction about 3D Hubs. 3D Hubs, as you may know, is an online manufacturing platform where we specialize in 3 technologies: 3D printing, CNC machining, and injection molding. What a lot of you might not know is what happens on the behind the scenes when you place an order. So when you go to our platform, you can upload your parts and you can select your technical requirements. And then we will give you an automated price, instant price in a few seconds. And that pricing is based on an AI engine that has analyzed more than 2 million parts. We will also give you design feedback in order to ensure that your parts are manufacturable. After that, every order that you place is auctioned in our network of manufacturing partners. This way, we can ensure that you will get the best price at the best lead time, and also without hassle and without risk. We are taking away all the risk from the manufacturing process from you. So as I mentioned, our 3 technologies is CNC, 3D printing, and injection molding. These are available on our checkout, and you can get an instant code for them. But apart from these, we have a large range of other 3D printing, other manufacturing processes that span the whole range of most manufacturing needs. In order to get access to them, you have to contact us directly by sending an email at sales@3dhubs. So what was the point of this intro? I just wanted to make you understand that we are here to help you bring your project into life. We are not biased towards any manufacturing technology, and we will always propose to you the best solution for your project. And Dylan and David and I, we have seen a lot of parts coming our way, and we have supported companies throughout their design process. And we're here to give you the most accurate information for you. Today, we're going to speak about 3D printing, and I will start with a small introduction about the trends. So apart from manufacturing, a core activity of 3D Hubs is educational content. We prepare a lot of content to educate engineers in order to get the most out of the available manufacturing options. In the beginning of the year, I worked on a report that covers the 3D printing industry. And today I'm going to discuss with you, I'm going to present to you some of the key findings of this report. So I started by reviewing the news that I saw on that were covered on the online media. And a key trend that emerged was that 3D printing is now ready for production. Companies like BMW and Adidas are using the technologies in order to produce end-use parts. For example, BMW released this metal bracket that is going to be used in a commercial car that is, I think, released now. And also, Adidas last year, they released a small small run of their shoes, sneakers, that they use 3D printed midsoles. And that is, for me, a signal that the technology is maturing to the point where production is possible. Another key trend is materials. Until recently, a major pain point for a lot of engineers was the lack of knowledge of the material properties of the end-use part. That is slowly changing. For example, we see that ASTM is releasing standards that will ensure the quality of parts produced with metal 3D printing technologies. And also companies like Desktop Metal and HP are working towards new processes that will produce parts that have material properties that are identical with traditional manufacturing processes. And this is another huge step forward towards a larger adoption of 3D printing. A third key trend from big industrial players is that 3D printing is now getting integrated into the supply chains. So, for example, HP, which is a printer manufacturer, uses their own technology in order to produce parts for their own internal supply chain. Also, companies like Whirlpool or aircraft manufacturers like Lufthansa and Airbus, they're integrating 3D printing in their supply chain for after-sale parts and spare parts. And an idea that is emerging now is that a lot of engineers are thinking not of designing only for additive, but for designing for both traditional and additive manufacturing. This way, for example, you can produce this part with injection molding in the thousands, and then later, during the later stages of the product life cycle, you will use selective laser sintering to produce the spare parts on demand. And that can lead to enormous economical savings. But this is how the technology is depicted in the large media. In order to understand better how the average engineer is using 3D printing in their everyday life, we did a survey. We sent a questionnaire to 400 businesses, and we asked them a few simple questions. One of them was, how do you use 3D printing? What is the end use? And unfortunately, only 40%, less than 40% of the engineers actually would even consider 3D printing as a solution for end-use parts. And from them, 60% will not produce more than 20 parts using 3D printing. And almost all of them would never consider it for productions of more than 100 parts. This signifies that this tells me that in the public, 3D printing is still not yet ready for production. Another trend that we see is that the demand for plastics is much higher than the demand for metals. Plastics, actually, they dominate the online demand. And that is because the technologies are mature and they can scale well to larger productions that go to the thousands. On the other hand, metal 3D printing is still quite expensive and only finds niche applications, and that hinders the wider adoption. So the key takeaway from this section is the following. What you see in the news is not what engineers do in their everyday life. And in order to take advantage of the technology, you have to design for it. And that is what we will see in the next section, which I will talk briefly about the do's and don'ts for additive manufacturing. I will not focus on any technology in particular, but I will cover the wider trends that you should keep in mind when you design for the technology. So, first of all, what happens to existing designs? it is actually very rarely a good idea to send a part that has been designed for another manufacturing process to print. And there might be several issues. Firstly, manufacturability might not be feasible, but most importantly, the cost will probably be higher. For example, recently we have received an order from a customer that requested 300 parts for 3 different designs, and the price that we could get for DMLS 3D printing, which is a form of metal 3D printing, was actually double than the price per unit that we could get for CNC machining. And that is because of economies of scale. As in the graph, you see the unit price of a typical part depending on the quantity. And the blue line is additive manufacturing, where the unit price drops in higher volumes, but not as much and as fast as the other 2 technologies, subtractive and formative technologies, for example, CNC and injection molding. And that is because the cost per part does not really change much for 3D printing processes. But there is always this gray area between 100 and 500 units, where 3D printing can compete head-to-head with traditional manufacturing. And that will be the focus of the next section, where we will talk in depth about these applications. Another thing that I want you to consider is support structures. Take a look on this video and tell me what you see, or better, what you don't see. This is the video from BMW that they're making to produce this metal bracket for their car. And what is missing here is support structures. So support structures are required in many 3D printing processes because, for a simple reason, you cannot deposit material on thin air. For metal printing, they play a different role. They also are required in order to anchor the part onto the build plate. And support structures, though, are the bane of 3D printing when it comes to production. They require manual post-processing to remove, and manual labor, and extra material, of course. And that means that the cost is increased drastically. So when you design for additive manufacturing to go to production, the number 1 priority for the designer is to minimize the need for support structures. And you can do that by taking into account the print orientation and setting a threshold in the angle that you use relative to the build plate. Another key aspect that you should consider is post-processing. This is the Bugatti caliper, the car caliper that is quite famous on the internet. And these are the images that you might have seen, the product images. But this is how it comes out from the machine. There is a lot of powder involved, a lot of support structures, and there is a lot of post-processing needed in order to achieve the end-use part that you saw in the previous slide. So there are, of course, necessary post-processes like support removal, which are important also when the part has internal geometries like internal channels, but also powder removal. And there are secondary operations like heat treatments that are needed to ensure the good mechanical properties of the part, as well as surface finishing, CNC machining of key features like this one. And that is just for metal. When it goes to plastic 3D printing, for example, with selective laser sintering, whether tightness or dyeing is another key post-process that is very often needed in order to produce an end-use part. So how can you design successfully? You should consider the lightweight. Lightweighting is key for several reasons. Firstly, it produces optimum structures, but also these structures are both light in weight and high in stiffness, so they produce parts that have higher efficiency, but also they speed up the printing process, use less material, and make sure that the part is manufacturable. There are 3 different strategies that you can adopt here. The first and most crude is lattice structures. So you get an existing design and you apply this pattern to remove material to remove most material. This reduces the weight but does not ensure manufacturability. The next and more advanced strategy is topology optimization. In topology optimization, you use simulations in order to end up with the optimum design. If you want to go a step further, another technique you could use is assembly consolidation. This is mostly a manual process, though, as you need to reconsider the whole assembly. So, for example, this part on the lower part of the slide, it's a satellite that used to be made from 30 different parts, but with 3D printing, now it is manufactured with a single part. Another thing, the last thing that you should remember is that 3D printing can create structures that no other manufacturing process can produce. And in order to take full advantage of the 3D printing processes, you should always consider adding the extra functionality to your designs. Some examples of this extra functionality are internal channels that are very common when you manufacture tooling for other processes. For example, molds for injection molding. Or they are very common also when you create heat exchangers. These heat exchangers have maximum surface, optimizing their performance, but also they can act as structural elements, creating overall products that are lighter and better. Another unique ability of 3D printing comes to when you are going to create organic structures. For example, this is the hip implant that is the first commercially viable mass-produced metal part produced with 3D printing. And this is today implanted in tens of thousands of patients globally. Here's another pro tip. A lot of times, when you see 3D printed parts, you notice that the holes have a cross-section that looks like a diamond or a teardrop. And this comes back to supports. These structures are self-supporting. They don't need any support structures to be manufactured. On the other hand, a circle will need support on the top of the circle in order to ensure good manufacturability. So the key message from these slides is this. I want you to remember that in order to take full advantage of 3D printing, you must always design for the process. So that brings us to the last section, where we will go through the options that you have today in order to create end-use parts using 3D printing. There are 6, in my opinion, there are 6 different processes that you could use, and I will give you some examples of for each of them, and that you can use as inspiration for your own projects. But first, what is an end-use part? Here's the definition that I'm using. An end-use part is something that is either sold as a product or part of an assembly of a product, or that is placed in service within a company's internal operations. So when you select a process to manufacture such a part, you have some technical requirements, And also you have some selection criteria that are mainly economic based. So there are these 6 processes that I think should be considered today for 3D printing. And let's start with FDM or FFF. FDM stands for Fused Deposition Modeling, and is today the most common 3D printing process that you can encounter. It works by extruding plastic material through a heated nozzle, and you build this way the part layer by layer. It is easy to use, widely available, and that means that the lead times that you can get are short, and the parts that are produced are very economical. The materials that are available are mostly commodity plastics that are used for prototyping purposes, but also there are engineering thermoplastics and composites that can be used for more advanced applications. Here's a case study, a use case that I think is ideal for FDM 3D printing: jigs, fixtures, and other brackets. These such parts, they have mostly medium to low mechanical strength requirements. They need to be durable, but thermal stability, for example, is not necessary. So when you would go to manufacture such a parts, you would have different options. You could use FDM, or you could CNC machine them, or potentially, in some cases, you could go to sheet metal fabrication. In order to produce a part like this in the image, the price that you would pay depends on the quantity. So, for example, with FDM, something like this would cost you around 60 to 20 euros, while for CNC machining, if it would be a one-off, the cost will be around 120 euros, higher cost. But when you increase the quantities, when you go to the tens or hundreds of this part, the cost per part falls drastically to 10 to 15, 20 euros in this range. And this is because of the economies of scale. Sheet metal fabrication follows a similar trend to CNC machining. And that means that after you cover your initial cost, the setup costs, the unit price falls drastically very fast. But ideally for FDM, if you need something fast and your quantities, you need to produce less than 50 parts, FDM is the ideal process. Another very important use case for FDM comes for medical applications. So these parts, they need to be sterilizable. And in order to do that, you have to put them in an autoclave. In order to survive the autoclaving process, the parts have to have high mechanical strength, and they also have to be heat resistant. In these situations, materials like ULTEM or PIC are ideal. And in this case, FDM 3D printing is the most economic process. PIC as a material is usually expensive. That means that even if you want to create hundreds of these parts, buying the stock material for CNC or the pellets for injection molding will be costly. And FDM can produce very similar results, very accurate results, in really a fraction of the cost in these cases. So this is our graph again, and now we can add the details for FDM. So FDM can be used mainly for internal operations. It's not really suitable for parts that are going to be sold to customers. And it is a very valid alternative to CNC machining, vacuum casting, and sometimes injection molding. But ideally, it should be used for quantities up to 100 parts. It is possible to scale in higher quantities, and we have seen orders in the magnitude of thousands, but this is not the key strength of the technology. Let's look at the second process now, SLA or DLP. SLA produces parts by solidifying a liquid resin using an ultraviolet light source. The strength of technology is that it produces parts that have smooth surface and high detail, and they resemble in appearance injection molding parts. On the other hand, though, they require a lot of support structures, and that may hinder their application in larger quantities. The materials available are thermoset resins, which tend to be more brittle than thermoplastics. But there are also other materials that are engineering grade. And the resins are available both in color, but also clear resins, which is important in some applications. For SLA, I have one key use case in mind, and that comes in the form of mass customizations. These razors in the photo are a result of collaboration between Formlabs and Gillette, and they managed to produce custom handles for these razors and offer them at high volumes. And when it comes to customization, the quantity that you're looking at is in the order of a few tens, up to 30 parts usually. SLA in this case can produce these parts very effectively, cost effectively, especially considering the complexity of the geometry. Because this part has a very complex shape, you would need CNC machining with 5 axes in order to produce it. Injection molding would not be an option as the quantities is only a few parts really. But vacuum casting, which entails the molding of a thermoplastic of polyurethane or rubber into a silicone mold, is an option that should be considered. But vacuum casting is also a manual process that follows a trend similar to 3D printing. It does not scale very well in larger quantities. So the unit price is still very high. So in these cases, SLA is the best process. And when you need to produce a lot of components that are customizable and have a finish that looks like injection molding, it's the best bet. Let's go to SLS. This is one of the industrial processes that is capable of production. SLS works by SLS uses a laser in order to sinter selectively, layer by layer, powder particles, plastic particles. These are usually nylon that can be also enhanced with other additives like glass beads or carbon in order to improve the properties. Nylon is an engineering plastic that has excellent strength and very good chemical resistance. One of the key benefits of SLS is that it does not need support structures. That means that you can nest multiple parts into the built volume and take advantage of economies of scale. Another process that is very similar to SLS is MJF, material multi-jet fusion. And that is the process created by Hewlett HP. MJF, instead of using a laser, uses ink and a heat source to sinter the parts layer by layer. This way, you can actually achieve higher productivity, and that is the reason why in most cases MJF will be more economical than SLS, especially for larger volumes. So what is the use case of MJF? In my opinion, MJF is a valid competitor to injection molding, especially for quantities below 500. Most of injection molding suppliers have a minimum order quantity threshold of 500 units. Below that, there isn't really any other manufacturing process that can be used until now. So When you need to produce parts in the hundreds, MJF is the ideal process. Another competitor would be vacuum casting, but again, the manual nature of the process would not scale well, meaning that MJF and SLS are really the way to go. So SLS is ideal for low-run production of plastic parts, and it's an alternative to injection molding and CNC machining. This brings us now to the metal 3D printing processes, and we will start with the most established at the moment, which is SLM or DMLS. SLM and DMLS work in a similar way to SLS. They use a laser to sinter layer by layer metal particles. Because of the temperatures developed during the process, though, support structures are necessary in order to anchor the part to the build platform. SLM and DMLS have fewer design constraints than traditional manufacturing, but there are still a lot of constraints that somebody has to take into account when you design for these processes. They offer high accuracy and high performance materials, and that cover the whole span of the engineering spectrum. There are two key use cases for these technologies. One is optimized brackets, optimized parts. The bracket on the photo was designed by a formula student team in the University of Delft, and it has been topology optimized. This means this geometry would not be manufacturable directly using CNC machining, and that is because it's organic. It creates these organic structures that they would require a lot of machining time. Nevertheless, with few design changes, if you wanted, you could manufacture a similar part with CNC machining. And the cost of that part would, in principle, be lower than what you would get with SLM. But again, the performance of the SLM part will be higher. Investment casting is another process that one could consider, and this process uses wax to create the model, which you then use to create the mold, and you pour metal inside that mold. That process is relatively cheaper than metal 3D printing, but the results that you get in terms of surface finish are generally lower. An ideal use case for SLM comes in the form of parts with internal channels, internal geometries. These are the most common application that we would recommend SLM to our customers today. These parts are really cannot be manufactured with any other process. Maybe investment casting. Investment casting would be an option, but again, the fidelity of these structures makes them probably not manufacturable. So DMLS, in short, is used to produce high-performance parts that can have either high mechanical strength or internal channels. Then there are two more metal 3D printing processes that one would consider that are up and coming at the moment. The first of them is metal FFF. Metal FFF uses principles similar to FDM to build a part, which consists of a mixture of metal particles with binding agents. This is the green part that is not metal yet, and it needs to be sintered in an oven in order in order to remove the binder and produce make the metal particles to bond together. This is a promising process that is easy to use, and it's based on metal injection molding, or MEM, which is a very common process for creating mass-producing metal parts that is used a lot in the automotive industry today. The materials that are currently available are mainly steels, so stainless steel and tool steel. And the printers are produced for mark forged and desktop metal. Since these systems have only been released for a few months now, it is difficult to know with certainty what the end cost of producing these parts will be. So take these numbers with a grain of salt. But this assembly on the left side could potentially be manufactured in a few days, in half the time than you would spend for CNC, that would need to spend for CNC machining, and potentially the cost would be very competitive to CNC, especially for lower volumes. Another way that you could manufacture such a part would be with sand casting. Sand casting, although produces very geometries that are relatively crude and not accurate, so CNC machining would be required. And also it's a laborious process, it's a manual process. You break the sand mold every time after you produce the part. So it does not really scale very well. To summarize for this technology, again, you would use it to produce parts for internal operations or internal service. And it's a very competitive technology to CNC machining and sand casting. The last technology that you should consider is binder jetting. Binder jetting uses similar principles as metal FFF to post-process and sinter the part. But it uses a different printing step. In metal binder jetting, the binding agent is jetted directly onto a metal powder to produce the green part. And this means that you can it means that you have similar manufacturing capabilities as SLS. You can go to batch production. It does not require any support structures during printing. Some support structures would be required during sintering. But since you don't need any support during printing, you can really stack the parts inside the build volume to fully utilize the machine. And that makes it very competitive with die casting and metal injection molding. So similar to SLS and MJF, metal binder jetting has great potential to be used for productions at the hundreds, around 100 to 500 units. The lead time potentially is much shorter than that for metal injection molding and die casting. But at the moment, the technology is not very widely available, so the numbers might be off here. And this completes our map of all the technologies that you should consider. And if you want to see how 3D printing can be used today and get an accurate pricing for your parts, you can visit our platform where you can use our tools to get an install price. And here you can select the material, but also the quantity. And we will show you very fast and efficiently, how the price changes depending on the quantity that you will choose. And this, before we close this presentation, I would like to summarize everything. So firstly, I want you to remember that there is no single coverall solution. When it comes to 3D printing, there are multiple processes that each of them are ideal for different applications. Also, I want you to remember that what you see in the news is not this is not how the average engineer uses 3D printing today. And thirdly, if you have any requirements or questions, 3D Hubs is here to help you simplify your sourcing process and help you select the best manufacturing solution for your application. And I think this is the end of the presentation, and we will be available now to answer some questions live in the air.
Yeah, so feel free to post whatever questions you need on the chat.
Okay, so Arkeos, one question, for example, was how do we estimate manufacturing costs?
So I assume that the manufacturing cost, I will answer generally about every process. So the cost for manufacturing depends mainly on three aspects. One is the material that is going to be used. So one is the material cost, the other is the machine cost, how long it will take to print, and the third is the post-processing cost. How long and how much manual effort will it take to finish a part? So the best way for you to estimate the cost of your parts would be to upload them on our platform. This way, we are going to give you an indication of the real cost. We are updating our algorithms periodically in order to use the most up-to-date data from the real-time 3D printing market. And while you optimize your parts, always keep in mind that lightweighting is key, as I mentioned in the presentation. And remember that the less support structures that your parts require, the cheaper they will be to manufacture.
All right, then another question on the chat was, what is the main problem for metal 3D printing? Is it rather high cost or quality of the product?
Most of the parts that we see that come to us when it comes to metal 3D printing, they are for the DMLS and SLM processes. These processes have really high cost when it comes to materials. So, for example, about a kilogram of powder can cost approximately $500 and upwards. This means that you should only use these processes when you have really designed for these processes. You have to optimize it. You have to optimize your structure for minimizing the need for support structures, or you have to have a part that requires DMLS that cannot be manufactured with any other process. So, for example, internal channels is a great application for DMLS. In all other cases, though, CNC machining or sheet metal fabrication are a better option. And we will recommend you these processes when you request a code on 3D Hubs.
Hugo Swift, he also asked, what kind of precision is possible with DMLS with mating parts? To what tolerances can you have hole and shaft fits, for example?
Well, this depends greatly on the print orientation and the way that the part is designed. So I think the standard tolerance that we use on the platform would be in the order of plus minus 1%. I think on each dimension, 1 or 2% per each dimension. I will have to check this up. But with DMLS, you will never get as good accuracy as you would get with other manufacturing processes. So, for example, CNC machining. And if you look at the parts, some of the parts that I saw in the presentation, a lot of them, they have been finished later using CNC. For example, the holes, when you have a hole or a thread that needs accurate dimensioning, these are most often machined after printing in order to ensure the accuracy of these features.
Okay, Imani asked, if I only want an iteration to be approved first and manufactured later, can we get a quote for that?
What we offer on 3D Hubs, we offer the design verification program. This means that if you have an order in the magnitude of 100 or parts or a larger production volume, what we will do is we will manufacture a few of them first and send them to you as samples for approval. So this is essentially a program that is identical to first article inspection program that you might encounter in other companies. So to answer your question, if you have larger production, send us the parts. We will make arrangements to send you some samples first that you can use to change your models and improve your designs before we go to production. And that applies to all of our processes, 3D printing, CNC machining, injection molding, and the rest.
Okay, then Hugo, he asked as well, we use nylon SLS for production parts, but we find the material scratches very easily, which affects customer satisfaction with the brand new product. How can we get around this issue?
That's a good question. So scratches happen because the material is soft. So a way that you could go around this issue would be to apply some post-process on it, on the end part. And I've seen there are some processes that are possible to increase the water tightness of SLS parts, for example. And that happens by impregnating the SLS part with resin. And this might also solve the issue with scratching, but we will have to examine this in a later section. So please send me an email with your parts and we can discuss offline.
Simeon is asking, does the 3D Hubs platform provide optimized build orientation or recommend some build orientation?
So on 3D Hubs, you can either you can select your own print orientation. So if you have designed the part with a certain orientation in mind, you can select that on the checkout. If you don't do that, then our manufacturing partners will probably pick up on the best orientation and they will place the part on the build platform the best way possible in order to minimize support distractions and ensure manufacturability. So to answer the question, if you have an orientation in mind, you can specify it. If you don't, we are working on new tools always to improve the design feedback that we have. But our manufacturing partners are also experts in their fields and they can orientate the part the best way in the build platform.
Little Johnny is asking, which type of printing is ideal for end use that has high strength, such as a bracket?
That is a bit of a question, a bit generic question. So there are a lot of other requirements that one should take into account. So for example, if you require, if metal is required, then DMLS would be the way to go at the moment. But soon metal FFF and the binder jetting will be an option. But CNC machining is always a very good option when it comes to creation in brackets. And if the part is not topology optimized or does not really need the design freedom of CNC machining, then of 3D printing, excuse me, then CNC would be a better solution for you.
Okay, then Shibin Babu asks, which softwares are best for topology optimization?
I can recommend two different software. I think my personal favorite is the products from Altair, and their software is very intuitive and quite easy to use, and you can optimize your parts not only for 3D printing but other manufacturing processes. And also know that Fusion from Autodesk offers design optimization, topology optimization capabilities, and Fusion also has a very good, is a very nice package for all-around CAD software. So these are the two that I would recommend. Look into Altair software firstly, and then if that doesn't fit your needs, I would recommend Fusion.
Imani is asking, do you have a chart showing specs for heat and strength tolerances for different materials?
That depends on the application that you have. We have online resources with a lot of articles that cover a lot of basic information and most of the information that you will need, and we will give you guidance to get you towards the right direction. And I would recommend you to go check our knowledge base, where I think there are a few articles related to this aspect. And also we have other material online that you could use. But if you have something specific in mind and you have to achieve some certain heat specifications, please send us an email at sales@3dhubs, and we will look into your case. I think we have time for one or two more questions. Two more questions.
Yeah. David is asking, which market is 3Hubs focusing on at the moment? Is it solely North America, or do you have partners through Europe or Asia?
That's a very good question. So 3Dhubs has a global footprint. So our main markets are actually the US and Europe. We have equally as many customers in both of these regions. But we also have coverage in Asia, like Australia is another region that we are servicing, and some other customers in the rest of Asia. And to answer your question, at the moment, we are in the process of updating our platform for our European customers. This update has gone already through for the US, and now soon our European customers are going to have the same experience on the platform.
Thanks. Jerome is asking, how could you help selecting the proper material and printing process for specific strength parts?
I assume that specific strength parts means that you have some requirements in terms of strength. A key thing that you should remember is that most of the 3D printing processes do not produce parts that have fully isotropic properties. So in one direction, the Z direction, the direction of printing, they will be weaker. They will have approximately, it depends on the process, but they can be from 5% to 20 to 30% weaker on the Z axis. That means that you cannot really treat these materials the same way as you would treat a traditional a traditional material in traditional sense. So part orientation is crucial there. When it comes to selecting the right material, you can follow a similar process with selecting a material for any other manufacturing process. So set the requirements in terms of tensile strength or other strength, and then we can help you with the available options.
Thank you. Another very interesting question from Jerome, which will be the last question as well. What is the minimum effort required to educate engineers so that they start considering additive manufacturing?
That is a very nice question. So, considering additive manufacturing education is actually becoming much better as time passes. So there are a lot of courses and workshops online that you could follow, but also another excellent place to start is the handbook that we offer with 3D Hubs. So if you go to 3dhubs/book, you will 3dhubs.com/book, you can find and download a sample copy of the first few chapters of the book. And then we offer the book also in very competitive pricing. That would be, I would say, the minimum effort that you would require. And also we have a lot of other educational material online that you can find on our knowledge base at 3dhubs/knowledge base. And we offer all of them, of course, for free.
All right, that's it. That was the last question. Thank you very much, Archaios. I think that was a great start to our webinar series. I hope you all enjoyed it and you tune in to the follow-up webinars. The next one will be held by Dylan and will cover injection molding.
Thank you all for participating, and we are looking forward to seeing you to the next webinars. And we will have a webinar in 2 weeks for injection molding, and the third one would be presented by David about CNC machining and how you can use this technology to the fullest. Thank you very much.